All right, welcome everyone to today's TCS Plus Talk. I'd like to remind people that we have a form to recommend speakers in case you want to see any particular talks. In particular, we have next week scheduled with Nathan Klein from University of Washington, who will be speaking about new algorithms for traveling salesman problem. But the following weeks are still indeterminate, so stay tuned to see what we have for that. But today we're very lucky to have Sepideh Mahabadi speaking about non-adaptive algorithms, or sorry, non-adaptive adaptive sampling in Turnstile streams. Sepideh is a research assistant professor at TTIC right now. Before that, she was a postdoc at the Simons Collaboration on Algorithms and Geometry at Columbia University. And before that, she did her PhD at MIT. Her research is focused on sublinear algorithms for massive data, including many different areas, including high-dimensional computational geometry, streaming algorithms, sublinear algorithms, sketching, as well as graph algorithms. Besides all of this, she's also been very successful in programming contests, including a gold medal at the IOI and placing highly twice at ACM ICPC World Finals. But without further ado, I'm going to pass it off to Sepideh. Sepideh, please share your screen.
So, do you see it?
Yes, that's fine.
Great. Okay, hi everyone. Thanks G for the introduction and thanks for inviting me and thank you everyone for joining the talk. So today I'm going to tell you about non-adaptive adaptive sampling on Turnstile streams. It's a joint work with Ilya Razenstein, David Woodruff and Samson Zhu. Okay, so what is adaptive sampling? Adaptive sampling, okay, is an algorithmic paradigm for solving many data summarization tasks. So in short, suppose that you are given a set of n vectors in a d-dimensional space. And what adaptive sampling does is that it samples every vector with probability proportional to its norm or norm square. And it actually does it in an adaptive fashion, meaning that once it first samples one row, then it projects away all the remaining vector from what it already sampled and continues on the residuals. Okay, so it projected onto the subspace orthogonal to what it has already picked. Pictorially, for example, if you have these 5 points, maybe in the first round, it samples the point that has the highest norm, and then it projects all the remaining points on the subspace that is orthogonal to what it's already picked. And then it continues on this subspace. So now we have these points, and we will again sample one of these points with probability proportional to its norm. And maybe this time, this point is sampled, and then we continue by projecting away again from it and sampling another point. So it does it for k rounds. And it's used in many data summarization tasks. So let me define a general framework for these tasks. So suppose that you're given a set of a matrix, which is n by d. So this corresponds to a set of n vectors in a d-dimensional space. For example, this could correspond to feature vectors of a set of objects in a very large data set. And so what is our goal? So given a parameter k, we would like to find a small representation of this data. So basically a representation of size k, and we would like to optimize a predefined function. So many standard problems fit into this category. For example, in the row or column subset selection problem, the goal is to find a subset of rows of size k that best approximates this data. What do I mean? I mean that's the total distance of what you have not picked from the subspace spanned by the rows that you have picked should be minimized. Okay. In the subspace approximation, the goal is to find a subspace of dimension k that best approximates the data, again, minimizing the total, the sum of the squared distances of all the rows to the subspace. In projective clustering, you want to approximate it with k, let's say with s subspaces of dimension k, and so on. And finally, for the volume sampling, the goal is to pick a subset of rows of size k that have the maximum volume. And by volume, I mean the volume of the parallelepiped spanned by those k points should be maximized. And why people care about this volume is that because it's one way to capture the notion of diversity. And in fact, we would like to reduce the size of the data set while maximizing or maintaining its diversity. Okay, so for this adaptive sampling has been used to derive approximation algorithms for all of these tasks. And so here, let me then define adaptive sampling more precisely. So in the first round, we would like to sample a row of the matrix with probability proportional to its squared norm. So basically the probability of sampling the ith row is going to be the norm of AI squared over the Frobenius norm of A squared. And the Frobenius norm is just the square root of the sum of entries squared, okay, in a matrix. So now in the subsequent rounds, we would like to compute the residual. So if I denote the set of rows that I have picked by the row, as the rows of the matrix M, then projecting away from this set of rows is equivalent to multiplying A, or each row of A, by this matrix A minus M plus M, where M plus is the pseudo inverse of M. Okay, so now for K rounds, we would like to sample every row with probability proportional to AI to the squared row norm of this projected row AI. And we would like to append, and then after we sample it, we will append it to the set of rows M. So now this process seems inherently sequential because you're sampling one row and then you're computing the residuals and then you're continuing on the residuals. So here we would like to see whether it's possible to implement adaptive sampling in a non-adaptive fashion, meaning that we would like to, more precisely, we would like to run it in one pass of streaming. So let's see then or recap what streaming algorithms are. So streaming algorithms is one model to capture or to handle large amounts of data. And in particular, it's concerned with the scenario where the data is so huge that we cannot store it in the main memory. So the data is stored somewhere else on the disk, and then we only can make sequential passes over the data. And we would like to solve our problem on the fly, meaning that we would like to use small amount of storage. Okay, so by small, I mean sublinear. And the parameters that we care about here are space, number of passes, and approximation. Okay. So now our data here, our input to the problem is a matrix. So the matrix is huge, it's coming in a streaming fashion. Now we can consider two models of streaming, right? So one is row arrival, where the rows of the matrix come one by one in the stream. And the second is turnstile, where we receive updates to the entries of the matrix. So for example, we receive I, J, and delta, meaning that add value of delta to the I and J entry of the matrix. And delta could be positive or negative. So now, and for the purpose of this talk, I'm going to focus, for the purpose of the algorithms, I'm going to focus on the row arrival model, but I'll make it clear which results hold in the turnstile stream and which results hold in the row arrival model. Okay. So the problem, our goal here is to simulate adaptive sampling, this K-round process, in one pass of streaming. And in fact, I should also mention that many of these data summarization tasks were considered even in the initial results for the streaming setting. Basically, the streaming setting is used for large data set, and the data summarization is also used when the data is large. So they were, for example, giving even some like K-pass algorithms for some of these problems and so on. Okay, so in a nutshell, yes, we can show that it's possible to run K rounds of adaptive sampling in one pass of streaming, and here is the outline of the results. So first, we show that we can solve L2 and 2 sampler, find an algorithm for an L2 and 2 sampler with post-processing. So what's the problem here? So we are given a matrix A, that is coming in a turnstile stream, and we are also given a post-processing matrix, which is given after the stream finishes. Okay, so it's first we are given A in a streaming fashion, and after the stream, we are given the matrix P. And the goal is to sample an index which corresponds to one of the rows of matrix AP with probability proportional to the norm squared of AP. Okay, so So basically now we would, if you're wondering what this matrix P corresponds to, basically this corresponds to the projection that we are using in each round of adaptive sampling. Okay. So we show that, yes, it's possible to sample each row of the matrix with probability roughly proportional to its squared row norm. And so we can do it in one pass and space which depends on d, epsilon to the -1, and log n. So basically this, as I said, corresponds to one round of adaptive sampling. And I should also mention that it's impossible to return the entire rows corresponding to that index, because at the very end of the stream, maybe you receive an update which is very, very large to one row of the matrix. And in order to be able to return the whole row, you have to have stored all of it. So basically in sublinear space, you cannot hope to return the entire rows corresponding to that index. Is this clear? Okay. Okay, so now
I have
yeah.
Sorry, I've got a small question about the two subscripts. So it's L22. One of the two is the norm. What is the second one?
The second one is the oh, okay. So you're taking L2 norms for each of the rows, but then you're summing all these L2 norms, right?
Okay. Okay.
Yeah.
Thanks.
Yeah. Okay, so now, so we can also generalize it to like P. So we can also generalize it for P equals to 1. So meaning that we are now, we would like to now sample every row with probability proportional to its norm, not squared norm. So this is like where P goes into. But again, for the purpose of the talk, I'm going to focus on P equals to 2. Okay, now using this sampler, we show that it's possible to have this adaptive sampling in one pass of streaming. So basically, we show that it's possible to have so we show an algorithm that outputs a subset of size k of the rows with probability that is very close to the probability that adaptive sampling samples a subset of size k. So basically, the total variation distance between the distribution produced by our process and produced by adaptive sampling process is at most epsilon. Okay, and basically we can do it in one pass and space which depends polynomially on d k 1 over epsilon and log n. And we can also show that apart from this set of indices, we can also report a noisy variant of the rows. So basically, for each of the rows corresponding to each of these indices, we can also report some noisy perturbation of that row as well. So R1 to Rk, this we can also report. And then again, similar to before, it's impossible to hope for, it's impossible to have the actual rows of the matrix in our sampler. Okay. Okay, so then we show the applications of our algorithm in for other data summarization tasks in Turnstile stream. So basically, let me go over them one by one. Suppose that, so in the row subset selection problem, as I said before, we have a matrix n by d and a parameter k. The goal is to report k rows of the matrix that minimizes the error. So basically, the squared distance of all the other points to the, or all the other rows to the subspace spanned by the rows that we have picked. So now our, so what we want to do is that, so what we can show is that we can always find a subset of size k of the rows that approximates this value up to a factor of k plus, order k plus 1 factorial. And this is in fact the first one-pass Turnstile streaming algorithm for the problem. The space usage of the algorithm is polynomial in d, k, and log n. Okay. So previous results were either working in the centralized setting or the row arrival model. So we can show similar results for subspace approximation. So in this problem, we are given, the goal is to pick a subset of dimension k such that the total distance squared of all the rows to this subspace is minimized. And again, we can show order k plus 1 factorial approximation for the problem. And again, this is the first relative error algorithm on turnstile streams that actually are producing k noisy rows of the matrix. So we can reduce the approximation down to 1 plus epsilon at the cost of returning more rows. We can also have similar results for projective clustering when we would like to report k subsets, each of dimension k, that best approximates the data. And finally, for volume maximization, where the goal is to pick k rows of the matrix that maximizes the volume. And again, the volume is the volume of the parallelepiped spanned by those k vectors. Okay. So for this problem, we can show an algorithm that has approximation factor alpha to the k and times k factorial. And the space usage of the algorithm is going to be ndk squared over alpha squared. So then we somewhat matched this, so the only previous result for this problem was using corsets, and therefore it only works in the row arrival setting. And here we give the first one-pass turnstile streaming algorithm for the problem. And we somewhat match this upper bound with the lower bound. So basically, we show that any p-pass algorithm that finds alpha to the k approximation in turnstile arrival model requires omega of n over k p alpha squared space. So this is tied up to a factor of k cubed d in the space and k factorial in the approximation. And we can also show that if you want to, for volume maximization, any algorithm, any one-pass algorithm in the random, even in the random order row arrival model requires omega of n space. And we also show a competitive upper bound for it. We show that for c bits smaller than log n over k, in n to the 1 over c times d space, we can have an algorithm with approximation factor c times k to the power k over 2. And I should again mention that the previous result only provided k to the ck over 2 approximation in the same space. Okay, so let me move on to the algorithms. So let me first tell you what this sampler does. So again, the problem is as follows. We are given the matrix A in a streaming fashion and the matrix P after the stream ends. And the goal is to sample one row of the matrix AP with probability proportional to its squared norm. So our sampler follows the general approach for L2 sampler of a vector. So in this problem, we are not given a matrix, but we are given a vector in a data stream fashion. And then the goal is to pick one index of this vector with probability proportional to its value squared over its 2 norm squared. Okay, so so what's new here is that, first of all, we are going to generalize our approach for, from vectors to matrices. And second, we are able to, we need to be able to handle post-processing matrix P. Okay, so for now, let's ignore the post-processing matrix P. And so here is the general approach for our sampler. First, we are going to pick a value Ti for each row of the matrix with uniform probability. So for each row of the matrix, we are going to choose Ti that is uniformly, that is sampled uniformly at random. And then we're going to set the set Bi to be a scaled version of Ai. So basically Bi is going to be 1 over square root Ti times Ai. And now the point is that if you look at it, now the probability that the squared row norm of Bi passes the threshold, which is the Frobenius norm of A squared, is exactly the probability that we are looking for. Okay. So now what we can do is that we can run this process and see and find the index I or find the row I for which this event holds, right? And then return that row. However, so there are two issues here. First of all, there could be multiple rows passing the threshold. And second, this is only in the idealized setting. So we don't have in the streaming setting, we don't have access to the exact value of BI squared and AF squared. So we need to handle that too. Okay, so the first issue, so there might be multiple rows passing the threshold. So what we do is that we just simply increase the threshold by a factor of, say, C log n over epsilon. And so now the probability that one row passes this threshold becomes lower, but the probability that multiple rows passes this threshold becomes even lower. So we create a gap, and therefore by repeating this process roughly 1 over epsilon times, this will give us the successful probability that we are looking for. Okay, and then the second issue is that we don't have access to the exact. So now we are, instead of checking for norm of BI being larger than gamma times the Frobenius norm of A, sorry, the norm of BI being larger than the Frobenius norm of A, we're going to check for this higher threshold, the norm of BI being larger than gamma times the Frobenius norm of A. Okay, and as I said, the second issue is that we don't have access to the exact values of this norm of BI and norm of A, so we are going to use existing algorithms for count, sketch, and AMS, but generalized to the matrix setting. So we need to have a modified variance of these algorithms that works now for matrices instead of vectors. Okay, so let me only go over the count sketch. So here our goal is to estimate the norm of BI, which is the row of a matrix, but only for norms for rows that have large norms. Okay. So let's see what is vanilla count sketch. First, let's see what vanilla count sketch does.
Hi, Sepideh. There's one question. Clement Canon is asking, in the row arrival model, you do have the exact value of the BIs, the L2 norm of the BIs, but not the Frobenius norm of A, right?
So we are, we are looking at the Turnstile stream in general. So
he says thanks.
Yeah, sure. Okay, so now given, so what is count sketch? So given a stream of items that arrive in a stream, we would like to estimate the frequency of each of items. So basically the value of each of the coordinates in this vector. So what count sketch does is that it preserves a table, which is of size, so it has log n rows, so R rows, and B buckets, so B columns. And then these rows correspond to a set of R hash functions. Okay, so each of these hash functions map each of the coordinates I from 1 to n to each of these buckets. So many of the coordinates could fall into the same bucket. And it also assigns them a sign. So now if when a value fi comes, it will be hashed to one of these buckets. And then based on its sign, we are going to either add it or subtract it from the bucket. So for example, here, H1 maps Fi to the first bucket, and maybe the sign is plus, so we are going to add Fi to the content of that bucket. And maybe H2 maps Fi to, maps I to the fourth bucket, and maybe its sign is minus, so we are going to subtract Fi from the content of that bucket. And we continue it. So later on, when we want to estimate Fi, we are going to report the median of the estimates we get from the buckets that I is hashed to. Okay, and so it's known that the total estimation. It's known that if we do it, then the total error that we get is going to be epsilon times the L2 norm of F, and in an additive manner. So the difference between the true value and our estimate is going to be at most epsilon times the 2 norm of F. Okay. So now we just want to generalize this approach to matrices. So now instead of values of the coordinates arriving, we now have the rows of the matrix arriving, right? And so instead of each bucket now keeping only a scalar value, each bucket is now going to keep a vector of size D. Okay, so we receive BI, we again hash it as before. Now we have a vector, we just add it to the content of that bucket or subtract it from the content of that bucket, which itself is a vector of dimension D. Okay. So the space usage of the algorithm increases by a factor of d, because now in each bucket we have a vector of size d. And second, we can show similar estimates for similar estimation guarantees. So basically now the difference between the norm of the vector and its estimate is going to be bounded by epsilon times the total Frobenius norm of the matrix B. Okay. Okay, so this is a generalization of count sketch to matrices, and we just use it to get an estimate for the norm of the row BI. Okay, so now instead of checking our initial condition, which is a norm of BI being larger than gamma times norm of A, Frobenius norm of A, we are going to both estimate norm of BI and estimate norm of the Frobenius norm of A by modified variance of count sketch and AMS, and then we are going to again check this condition with estimations. Okay, and then we can show that this test succeeds with probability epsilon. So we repeat it and we get a sampler with the probability that we are looking for. Okay. So this gives us basically the result for the case where we don't have a post-processing matrix P. Now, suppose that we also have this post-processing matrix P, then it's very simple to adapt our algorithm to this case, because all the sketches used in this algorithm are linear transformations. So basically, in order to apply, so they're equivalent to multiplying a matrix S to our matrix A. So basically, these linear sketches is just equivalent to multiplying our matrix from left by a matrix S. Therefore, applying the sketch on AP is equivalent to applying the sketch on A and then post multiply it by P. Okay. And therefore, so what we do is that during the stream, we just maintain our sketch on the rows of the matrix or values of the matrix A, and then at the end we are receiving this P. We are going to multiply our sketch by P, and this is going to be a sketch for AP. And the space usage of the algorithm is going to be d over epsilon squared log squared of n bits. Okay, so this gives us the sampler that we want. So basically, we can now show that we can sample every row of matrix AP with probability proportional to roughly what we wanted. Is there a question? Or...
I have one question. So you maintain these estimates of the BIs, right? Mm-hmm. You don't have to do one for each of the data points, which would multiply your space usage by a factor n?
No, we are only, we are, so in vanilla count sketch, you're maintaining this estimate for the whole vector, right? So now the whole vector corresponds to the whole matrix, and each entry becomes like a d-dimensional.
I see. Okay, that makes sense.
And,
awesome.
and you're only reporting a good estimate for rows that have large norms, right? For small ones, you're not giving a good guarantee.
Okay, sure. Yeah, that makes sense. Thanks.
Okay, sure. Okay, so now let's see how we can use our L2 and 2 sampler in order to give an adaptive sampler. Okay, so basically we are going to, intuitively, we are going to maintain k instances of our sampler corresponding to each round of adaptive sampling, okay? And is there another question or no? Okay. So basically, what we do is that we are going to, at the end, so we are going to maintain these samplers throughout the stream. And then at the end, we are going to run adaptive sampling on the sketches that we have. So basically, we are going to use, in round I, we are going to use a sampler SI to sample one of the noisy rows of A with post-processing matrix P. And now this P corresponds to the projection away from what we already sampled. And then what we sampled, we're going to append it to the set of rows M. Okay, so now, so one issue is that, as we said before, we cannot return the actual rows. We are reporting some perturbation of the noise, of the rows. And this is fine because we are returning the samples, and we are returning some noisy variant of the rows such that the norm of the noise itself is smaller than epsilon times the norm of the residual that we wanted to report, in fact. So we are preserving the norms, we are roughly preserving the norms. However, the main issue here is that this noise is going to change the probabilities in this, of sampling in the subsequent rounds. And in particular, it could zero out some of the probabilities that shouldn't have been zero, and vice versa. Okay. So let's see an example. Suppose that we have two vectors. One of them is this long vector along x-axis, m and 0. And the second vector is a short vector orthogonal to it, let's say 0 and 1. Okay. So now with high probability in the first round, we are going to sample the first row A1. And although we are reporting a small perturbation of this row, but this, because the initial norm is large, then this perturbation may cause a lot of errors. So for example, if we return R1 instead of A1, we can see that now the residual norm of A1 onto R1 is still larger than the norm of the residual norm of A2, right? And in fact, we can modify this example so that maybe A1 is going to be selected again and again. Whereas if we had, if we didn't have noise and we had, in the first round, we had selected A1 itself instead of this noisy perturbation, then probability of sampling A1 again would have been 0. Okay. So this is this is a concern that we have, and this shows that we cannot hope for a multiplicative bound on the probabilities. And so, however, we show that this picture does not really happen. So what happens is more like the new picture, and this is because we can show that not only the norm of the noise itself is small, but also its norm is small in all directions, or in any direction, to be more specific. So basically, we show that for any projection matrix Q, the component of noise along that direction is bounded by an additional factor, which depends on the total decrease in the Frobenius norm of AP after we apply this projection onto Q. So roughly speaking, because count sketch is a linear transformation, multiplying it by matrix Q, resulting in multiplying the error by Q as well. Therefore, the noise goes down from epsilon AP, so which is the guarantee that we get from count sketch, to epsilon times APQ. And therefore, this means that the noise is going to be bounded in all directions, and in particular, the direction which is orthogonal to what we have, the true norm that we should have picked. Okay. And therefore, this allows us to bound the additive error of sampling probabilities in the subsequent rounds. So this is basically a lot of derivations. So I'm not going to go over it into details, but let me give you a high-level overview of what's happening. So suppose that our process, our sampling procedure, produces indices J1, J2 to Jk. And now we consider two bases, U and W. U is going to follow the actual rows corresponding to those set of indices. So basically, we are going to run the Gram-Schmidt process on the vectors, on the true vectors corresponding to these indices one by one to get our basis U. And then the basis W is going to correspond to the set of noisy vectors. So we run Gram-Schmidt process on the set of noisy vectors corresponding to those K indices one by one to get our basis W. And now we can, so at any time, we can write any of the rows of the matrix in terms of both of these bases. So basically, we can write for any row of the matrix AX, we can write it in terms of basis U with coefficients lambda xi's, or we can write it in terms of W with coefficients, say, Ci, Wi. Okay. So now the point is that, so the correct probability at time t, at iteration t, the correct probability that we should have sampled row AX with can be written very simply in terms of the coefficients lambda xi's. Because now projecting away from the true norms, we only get its last d minus t plus 1 coordinates. So basically, we only get sum of I from t to d lambda of xi squared normalized, but then normalized. However, what we actually sample from is a probability that can be written easily in terms of the xi's. Right? So this is projecting away from the noisy rows. And this will kill all the first t minus 1 coefficients of AX written in terms of basis W. So so the probability that we actually sample a row AX from is going to be the sum of I from t to d CXI squared. Again, normalized. So now, in order to show that the probabilities are not very different, we are going to bound the difference between these two sampling probabilities summed over all rows. Okay, and we actually do it by showing that the change of basis matrix from U to W is similar to identity matrix, and therefore we can bound the total variation distance by a factor of epsilon. Also, like when you have an error of epsilon in one round, it's going to get propagated in the subsequent potentially k minus 1 rounds that is coming. Because we have k rounds in total, we are going to get k squared epsilon times k squared times epsilon total variation distance between the probability distribution of our algorithm and the adaptive sampling. Okay, so by changing the variables, by changing epsilon to epsilon over k squared, say, we get our results for adaptive samplers. So we can show that our algorithm produces a subset of size k of indices such that the total variation distance between the distribution produced by our algorithm and produced by adaptive sampling only is bounded by at most order epsilon. And the total space usage of the algorithm is polynomial in k, 1 over epsilon d n log n. So if there's any questions, I'll, okay. Okay, so now let's see two applications of these results in the data summarization tasks that we discussed. Okay, so in these applications, like a main challenge is to show that it suffices to have a noisy perturbation of the rows instead of the rows themselves. So in the row, so let me recall. So in the row subset selection problem, so the problem was that we are given this matrix n by d matrix and an integer k. The goal was to report k rows of the matrix that have the that minimizes the error, which is the total square distance of all the remaining rows to the subspace spanned by the vectors that we have picked. Okay. So there are existing algorithms for the offline setting. So there are existing results showing that adaptive sampling provides a good approximation, basically provides a k+1 factorial approximation for row subset selection problem. Okay, so in fact, they show that volume sampling provides, so volume sampling is a process that samples every subset of size k with probability proportional to the volume of the points, volume of the parallel pipette, say, spanned by the points. And so volume, the results showing that volume sampling is providing a k+1 factor approximation for subset selection. And there are also results showing that adaptive sampling gives a good approximation, basically k factorial approximation for volume sampling. Therefore, these two results show that adaptive sampling itself is giving a good approximation for subset selection. And now here we show, and in fact we have already shown that our non-adaptive adaptive sampling gives a good approximation for adaptive sampling. So basically, we can show that for any set of indices, J, output by our algorithm, then if we denote R if we use R to denote the set of rows, the noisy rows corresponding to this set of indices, and M to be the set of true rows corresponding to this set of indices, then the total error corresponding, that is the total square distance of all rows project to the subspace spanned by R and by M are roughly equal. So the error for both of these are roughly equal with respect to a set of fixed indices. And then because we showed that the total variation distance between our algorithm and adaptive sampling is at most epsilon, for most of these indices J, we know that their probability are almost the same. And therefore, these two together show that for the purpose of the error of row subset selection, non-adaptive sampling is going to give a good approximation to adaptive sampling, and therefore a good approximation for row subset selection. Okay. So finally, this will give us an order k+1 factorial for row subset selection problem. So this was a somewhat immediate application of our results. So now let's look at volume maximization, which is which uses the components that we had here, not the algorithm itself. So basically, again, in this problem, we're given a matrix, which is n by d, and an integer k. And the goal is to pick k rows of the matrix A with probability proportional to their volume. Right, and for example, if we pick these two, if k is equal to 2 and we pick these 2 points, then this is the volume that we're getting. So it's known that the greedy algorithm provides a k factorial approximation for volume maximization. So in fact, the greedy algorithm picks, at each point, the greedy algorithm picks the vector that is furthest away from the subspace spanned by the points we have already picked. So in the first iteration, you maybe pick the, you pick the point that has the largest norm, and in the second iteration you pick the point that is furthest away from the line passing through the origin and the first point, and you continue until you get k points. Then it's known that this greedy algorithm provides a k factorial approximation for volume maximization. Okay. So now we would like to simulate the greedy algorithm here. So we are going to maintain k instances of count, sketch, AMM, and our sampler, L2 and 2 sampler. Okay, and so we are going to use it in k rounds of instead of k rounds of the greedy. So first we are going to use count sketch to find the row of the matrix that has the largest norm. So if the value of, if the norm of this row is large, then it means that the error in the count sketch is small, and therefore, therefore we can trust it, and we have found a true largest norm, or approximately largest norm. However, if the value of if the norm of the row that we have found is small, if it is more precisely, if it is smaller than this threshold, then maybe the error is large, but then we can show that there exists enough number of large rows that if we just sample from them using our L2 and 2 sampler, we will get a good enough row. Okay, so so now so this is, here we use the count sketch, and then in order to find the Frobenius norm of AP, we are going to use the AMS, and for sampling we are going to use our L2 and 2 sampler. And then, so we find a row either by count sketch or by our sampler, and then we are going to update our matrix P, which is the matrix projecting away from what we sampled, using our sampled row R. And then we continue this process. So this will give us an approximation factor alpha to the k times k factorial for volume maximization. And again, this is the first one-pass Turnstile streaming algorithm for the problem. Okay, so with that, let me conclude the talk. So basically here, we show that we can have a sampler, LPN2 sampler, that gives us like a small relative, 1 plus epsilon relative error plus a very small additive error. And the space usage of the algorithm is polynomial in D1 over epsilon and log n. And then using this LPN2 sampler, we showed how we can get our adaptive sampler by maintaining k instances of the PN2 sampler. And so the adaptive sampler that we show gives total variation distance, which is order epsilon. Its space depends polynomially on d, k, epsilon to the -1 and log n. And then we showed applications of these results to a set of data summarization tasks, including row subset selection, subspace approximation, projective clustering, and volume maximization. And further in the paper, we also show lower bounds and upper bound in the row arrival setting for volume maximization problem. Okay, so a few open problems here. If first of all, if we can get a type bound for the dependence on the parameters in our algorithm, so basically the space dependence on like the exact power of say d or epsilon. And second, if we can find further applications of this non-adaptive adaptive sampler. And finally, to give you a more specific question, so we don't know if the volume maximization result is in the row arrival setting is tight. So in particular, we show that if you want to get approximation factor c to the k for a specific constant c, then you would need omega of n space. But for example, what if I allow you to have approximation factor k to the k? Then is it possible to get a space that is, say, independent of n or have very small dependence on n? So we don't know that. And so that concludes my talk. And thank you all for joining. Yeah.
Awesome. Thank you for speaking, Sepideh. Are there questions from the audience?
I have a small question with regard to the projection matrix. Do you think you can use those because they are linear essentially? Do you think there are other kinds of transformations your techniques could possibly handle that are not linear? Maybe like something that's well approximated by linear or something like that?
Yeah, it's quite possible, right? If you can approximate it by a linear subspace, then I guess yes. It's a matter of whether we can bound the error, right? Yeah, I mean, it should be very dependent on the specific problem and how we are approximating it using a linear subspace.
Thanks.
Yeah.
All right, are there any other questions from the audience?
Hi, could you talk a little bit about the lower bounds techniques that are used, or like what kind of like, is it a combination complexity lower bound that reduces?
So one of them is from a reduction, using reduction from GAPL infinity.
Okay.
And the other one is from distributional set disjointness.
Okay.
So we construct these matrices that have, so in one case they have low, say, volume, and then in the other case we have this large volume produced by those. There exists a set of rows that give us like large volumes, and this is because, say, the vectors are orthogonal to each other, and then they correspond to see whether the two vectors are disjoint or not, and then this is how it relates to, for example, distributional set disjointness.
Oh, I see. Okay, thanks.
Yeah.
There's a question in the chat from Sepideh Agha Molai asking, what is the requirement for a problem to be solvable using non-adaptive adaptive sampling?
I mean, so for example, we show that here we are approximating volume sampling using our non-adaptive adaptive sampling. And volume sampling is used a lot in many of these tasks. For example, if we know that volume sampling is giving a good approximation for a problem, then we can use like our non-adaptive sampling as well. But a more general yeah, I think like whatever like adaptive sampling is a good approximation for, the non-adaptive should also give a good approximation. Yeah.
Awesome. Any more questions? All right, I think that might be about it. So if so, I'm going to take us offline in a second. If anyone else wants to hang out and chat with Sepideh for a bit longer, then that's an option. I'll mention again that next week, we are going to have Nathan Klein speaking on approximation algorithms for TSP problems. The week after that is yet to be announced. We're still looking for more suggestions if there's any talks you're really excited to see. So please suggest those on our website. And with that, I'll take us offline. Thanks for joining.
Yeah, thank you.